Paul Callaghan's my name. I'm from OLEOLOGY, based in Perth, Australia. We service the Asian region for water treatment. Today we're going to talk about PFAS, the latest emerging contaminant, which is of major concern to all island nations and for the health of people involved in the world. It's really only been in the last 20 to 30 years that people have become aware of its serious impact on human health. Let's go to some slides and have a look at how this is impacting on human health and the environment around the world. Welcome back. We're talking about PFAS, the health and environmental challenge, and as a result of that, the removal and waste generation. I'm Paul Callaghan, as a reminder, from OLEOLOGY, working with you here in Australia and Asia. OLEOLOGY has been engineering oil-free water, and we're talking today about PFAS. Now, PFAS is per- and polyfluoroalkyl substances. PFAS, most people know as a result of reports regarding firefighting foams and the chemicals that are associated with it. And they're known for their particular chemistry, which has a double bond between the carbon and fluorine atoms. Is that it's made its way into water, and we need to talk about that, the impacts on human life and the environment, but also then how we overcome it. And while we're talking about PFAS, it's not possible to consider how to treat PFAS if you don't also consider and the oil in water and the ability to remove the oil in the water, the organics that are often associated with PFAS. It's not found in nature, it's purely man-made. It has serious health implications. It's linked to several cancers. Very disturbingly, it's an endocrine disruptor. So that has an impact on humankind, but it also has a big impact on fish spawning and the fingerlings, basically the reproductive system, both in humans and in animals in nature. It's absorbed by ingestion, and impact of the forever chemical, as it's termed, for PFAS is in the order of 40 to 90 years. So roughly 2 to 4 generations before its half-life has been reached. They do break down and oxidize very quickly by comparison. Not only does it have a very long half-life in nature and in the environment and in our bodies, but there's no medical interventions able to remove PFAS from our bodies once it's been absorbed. The best and the only intervention is to stop the exposure. And that's what we're here to talk about today. In the oil and gas industry and the mining, in waste, rubbish, landfills, it's listed on the Stockholm Convention. Many of the countries from which you would be listening to this presentation today will be a party to the Stockholm Convention, aimed at reducing environmental disruption as a result of contaminants. In Australia, it's part of the National Environmental Management Plan 2. In the US, in legislation in 6 states, that will be enacted in the middle of this year coming, that's 2021. And European areas, they're looking to enact a complete ban on PFAS products, which is quite difficult because PFAS is found throughout a range of industrial applications and also very simple use, such as cardboard linings, paper bags. It's used in waterproofing and stain guard protection. It's an active ingredient in pesticides. Part of the process for the manufacturing of printed circuit boards, metal plating industries, firefighting foams is prevalent and still in use around the world in many locations. All of that finds its way down into the wastewater treatment plants, in industry, through the sewer system, into the wastewater treatment plants, which ultimately discharge into the river and to the ocean, finding their way into fish stocks, ultimately for ingestion by ourselves, Similarly, for waste, it leaches out the PFAS. PFAS is highly soluble and it continues to leach into water for a long period of time. That may find its way into the soil. The groundwater then continues its progression towards the river and ocean, and again ends up in fish stocks. The other issue, and I mentioned soil, is it finds its way into the soil. Plant roots manage to find the PFAS in the soil, in the water, that are bringing in the legislation of the PFAS under the PFAS umbrella that were known. A lot of IP still is protected around the PFAS compounds, and they're not disclosing what they are in understanding what is required. PFAS is found with hydrocarbons. And if we look at the brief history of our development and where we started about 16 years ago in working with air services in their fire training grounds, the PFAS that we were really seeking to remove was as a result of the AFFF firefighting foam, AFFF being aqueous film-forming foams. In that particular instance, the aqueous film-forming foam was used in conjunction with jet fuel to form the basis of the fire. Fire trainers, the firefighters, then as part of their training, quelled those fires with aqueous film-forming foam. All of that water, unburnt jet fuel, partially burnt jet fuel, and the AFFF foam made a highly emulsified mix of oily water that was chemically stable. So in order to treat that and make it safe for discharge to the environment, we had to achieve a discharge of oil in the water of less than 0.6 parts per million, or 600 parts per billion. That was the requirement back in 2004, the PFAS from the water. Subsequent work in 2011 at the Perth airport, treating groundwater with PFAS impaction, showed that we were actually removing the PFAS, particularly the PFOS and the PFOA, on analysis of the water. This led to further work with air services at Launceston Airport in 2012, continued on through to 2016 at Tullamarine Airport in Melbourne, where independent work was done on our treatment system by Becker Environmental at the behest of air services to ensure the veracity of all of the work that had previously been done. That was proved, and that discussions in Australian Parliament as part of the Senate's Estimate Committee hearing into methods, and to have a robust system, you need to be able to treat hydrocarbons, both in their free, emulsified and emulsified form. And we do that with MySelex. We're able to do it because MySelex has got the smallest footprint, very small cost of operation. Importantly, with treating both hydrocarbons and PFAS in association with those hydrocarbons, we end up with a minimal volume of dry waste. The waste needs to be considered in any form of treatment for PFAS. Sludges are expensive to treat, difficult to move, and ultimately very costly. Backwashing of systems also produces further concentrated waste, which also require costly treatment. The best and safest manner is a dry waste with the PFAS contained within it, which makes it environmentally safe. There's also, in our processes of treatment, no residual chemical, nor chemical dosing required. We have a fixed chemistry within our systems. All emulsions via cartridge filtering, which you can see as in the second picture, and the cartridge is portrayed in the middle of that oily water mixture, and on the right hand side in each of those pictures shows the water after discharge having been treated by the OLEOLOGY with the Mysolex treatment process. We're able to, from left to right, in decreasing size of oil droplet. Oil droplets of a 50 micron size are easy to separate out. As the oil droplet size decreases, it becomes increasingly more difficult for conventional equipment to remove that oil droplet. Mysolex spans the entire range. We remove and recover oil in its larger forms down to about 5 micron droplet size. And that's in the primary stage, the first of the red arrows. The second stage is able to remove oil and oily emulsions at a very smaller droplet size, down to about 4 microns in size, depending upon its state. And the final stage is the filtering stage, which is able to remove oil droplets down to 0.09 droplet size. We're getting into the heavily emulsified oil-soluble components, and it's in this stage and just beyond there that we begin the removal of the PFAS. It's important to understand that PFAS is at the highly soluble end, and unless you remove the other contaminants before it, your PFAS polishing stage, and there are a few conventional types of PFAS removal, such as granular activated carbon and ion exchange. Now, we've been involved in a number of projects where we've been approached by companies that have activated carbon and ion exchange resin that suffer premature breakdown and failure of the system that is leading to early breakthrough of PFAS because they have oily emulsions finding their way into their treatment system and they haven't been able to remove them by effective and robust pre-filtration. So the pre-filtering process to remove and discharge PFAS treated water down to the levels of parts per trillion. If you don't do the primary separation correctly, you will not successfully and commercially viably achieve the treatment for the PFAS. We consider that as an onion, progressively starting at the outer layers and removing the greater mass of oily waste or organics and progressively shrinking down the mass of production of contaminant until you get to the core of the onion, the very small part. And that small part is where we are targeting the PFAS reduction. So remove the outer layers, it's much easier to get to the inner targeted layer. In equipment on the ground, well, we put that into 2 containers, 2 20-foot containers. So imagine 2 20-foot containers sitting side by side, a footprint of approximately 6 meters long by 2.5 meters wide, so approximately 30 square meters. Fairly small footprint for something that can treat 8 liters per second, about 800,000 liters per day, and achieve a discharge that's below detectable levels when measured in parts per trillion. We have 1 pump, so it's very low energy. The systems are automated and have remote monitoring to infer the performance of the equipment. The small footprint I've already outlined, there's minimal service associated with it. There's no chemistry, there's no chemicals added to the process, and there's no chemistry that remains in the water from the process. So again, we reduce the risk of future liability as we do not add any chemical to the water. Our chemistry is fixed, it's non-leaching and non-toxic. Mysolex is hydrophobic, that is, it repels water. So when we remove the cartridges or the filtering media, it's dry. We're able to store those in small containers that are sealed and then sent for thermal oxidation. So we have a total treatment. We achieve a high in terms of footprint. The OLEOLOGY with the MySelex technology wins hands down on that. Far smaller than granular activated carbon and far smaller than ion exchange systems. The volume of flow relative to the size, MySelex is about a 20th of the volume of media that's required to achieve the flow rate. MySelex again is extremely good. There's limitations in GAC in achieving the short chain reductions of PFAS. Ion exchange, if selectively and correctly selected with enough of the contact time, can achieve those levels. It's a short and long chain hydrocarbons as well as short and long chain PFAS. So across the board and across all PFAS contaminants. And that's something that we really haven't spoken about. Of the 6,600 known, and that number's probably grown by now, of PFAS contaminants, we use TOPA testing, that's total oxidizable precursors assays, to ensure that the total of those known and unknown known analytes that can't necessarily be assessed by commercial laboratories at this point in time. We do those TOPA tests to ensure that that total range of carbon fluorine products are removed by the MySelex process. So we have compared to sludges and other wet wastes. Put that into comparison with an on-the-ground system. The conventional system is shown by the series of tanks and containers in place, in operation at an aviation facility here in Australia. By comparison to that conventional system, which employs granular activated carbon, the 4 red triangles would be the same footprint that is required to treat the same volume of water per day through an OLEOLOGY with MySelex system. And that's removing the hydrocarbons, the emulsions that are created as a result of surfactants formed from the AFFF firefighting foam, removing the PFAS from that water to be treated, and doing that to non-detectable levels here in Australia at 700 meters cubed per day. It's a much smaller system. Lower cost of setup, lower cost of operation, lower cost of waste. It makes it affordable for industry to enact, which is to make profit for the shareholder, and the requirements of environmental protection associations which want to protect the environment. It's bridging the gap between the two. The technology's here and available now. That's the basis of the system of removal. It comes in a stage sequence as shown via this graphic. It's applicable to the oil and gas industry, to general industry, to fire training, to mining, to groundwater. It has application for just about any operation. Through the first stages, we have no waste generation. They are the polishing stages, the 3rd stage and the 4th stage generate a dry waste. Again, safe and low cost of operation. Thank you for listening.